There are problems posted from last Friday that have been posted over break, and I know not everybody was, free to work on stuff the whole time. So I'm going to give you a very light number of problems this week. Mostly you'll just be working on the ones that I posted for last week. Okay, for the quiz this week. I'll try to do like one problem a day this week, and then plus the stuff that's already posted. In class last time we were working on this example. Actually, for the last 2 times we've been working on this. These can take a long time. We were working on a linkage problem. Where these are connected by a pin joint. I call these joints A, B, and C. And this was member 1 and member 2. And we had a 600 Newton force applied at the pin. Each member was 3 meters long and had a mass of 10 kilograms. And at the instant shown, there was no angular velocity. By the way, this is something that'll come up in these problems a lot. Notice that when you have an isosceles triangle like this, and I must have given angles and stuff. Is it equilateral at this point? Oh, 70. These are each 70. But notice that as this thing moves, it has to be an isosceles triangle all the time. And so you can't have one of those 2 members rotating faster than the other one. And so as this thing, all it can do is go in and out, flatten down or stretch out. And what you have to get is that the omega of this one is always equal and opposite to the omega of that one. We'll see that in a lot of examples. That's not going to come up in this problem, but really the way it came up for me was it comes up when you're designing these problems. It doesn't make any sense to prescribe angular velocities that aren't equal and opposite in a case like this. Okay, so what we got so far is okay, so what do we do? What's the process?
7-step process.
Yeah, so for each member, we do that 7-step process, and we come up with the rotational equation and Newton's second law as makes sense for each of those members. And then we count up the equations and variables and see where we stand at that point. So part 1, Newton's second law and the moment equation. So we got a first one that said 1.03 F12x minus 2.81 F12y minus 30 alpha 1 is equal to negative 756.3. And then we got a second equation that said negative F12x minus RC minus 10A2x, that's the acceleration of the center of mass of member 2, is equal to 0. And we got a third equation that says negative F12y minus 10-2y is equal to positive 98.1. And then we got a fourth equation that says 0.513 f12x plus 1.41 f12y minus 0.513 RC minus 7.5 alpha 2 is equal to 0. Okay, so we get those four equations from using Newton's laws. And what do we have for variables? We have F12, alpha 1, acceleration of the center of mass of 2, and then the scalars RC and alpha 2. So how many variables is that? 2, 4, 5, 6, 7. Okay, so we need 3 constraint equations. That is, as long as we can come up with our 3 constraint equations without increasing the number of variables at all, 3 is enough. So now we'll move on to part 2. That's the geometric constraints. So we already came up with 2 of those. What was the process that we used for those? That's pretty vague. I mean,
That's not wrong.
that's true. So yeah, what we did was our first 2 constraint equations came from the fact that at that pin A, the acceleration according to member 1, using the watermelon equation, is equal to the acceleration of A according to member 2, using the watermelon equation. So we express the acceleration of A from the pin B to A using member 1's angular acceleration and angular velocity. And then we did it for 2. Since that one doesn't have a fixed point, we did it from the center of mass. Okay, and those gave us 2 more equations, and that's where we left off. So our 5th equation of this system was 1.03 alpha 1 plus 0.513 alpha 2 minus a2x is equal to 0. And our 6th equation said negative 2.81 alpha 1 plus 1.41 alpha 2 minus a2y is equal to 0. And that was where we ran out of time last time. We need 1 more equation. So where's that going to come from?
There is no horizontal acceleration at the pin and slot joint.
That's right, exactly. So we're going to say that according to member 2, the acceleration at C the x component has to be 0. And why does the x component have to be 0? Yeah, right. The pin and slot joint, the thing can't move side to side. It can only move up and down. So the last one is going to come from the fact that at the pin in slot, the point C can't accelerate horizontally. Okay, so we need an expression for the acceleration of C, and we can do that as the acceleration of that point C relative to the ground is equal to the acceleration of that point C relative to the center of mass of 2 plus the acceleration of the center of mass of 2 relative to the ground. And this one we already have a name for. This one is what we're calling A2. the acceleration of c relative to the center of mass is equal to alpha 2 cross r plus this stuff that goes away because we don't have any omegas. Alpha 2. We have a variable, a scalar variable alpha 2, and the vector alpha 2 is given in this way with that scalar variable. So the last thing we need to do is come up with an r vector. We need a vector that goes from the center of mass of 2 to the point C. Yeah, and so I think that's going to be 1.41 negative 0.513 off the top of my head. I can only do it in my head to 3 decimal places because I'm rusty from spring break. I have it written here. Okay, so the acceleration of c relative to the center of mass of 2 is equal to 0, 0, alpha 2 crossed with 1.41 negative 0.513 0. And that is 0.513 alpha 2, and then 1.41 alpha 2, 0. Okay, so the acceleration then of c relative to the ground is equal to 0.513 alpha 2, 1.41 alpha 2, I'll leave off the z's now, plus a2x, a2y. And so our seventh constraint equation says that the x component of that has to be equal to 0. So 0.513 alpha 2 plus a2x is equal to 0. Okay, so now we have 7 equations for 7 variables, and we should be able to solve this. So our matrix, our augmented matrix, should look like this. Ooh, that was a cool sound. And I'll do it in this order. 1, 2x, 1, 2y, alpha 1, a2x, a2y, rc, alpha 2, and then these are the constants. So equation 1, we have 1.03 f12x's, negative 2.81 f12y, alpha 1, negative 30, And then the constant is negative 756.3. Equation 2, f12x, we have negative 1. a2x, we have negative 10. rc, we have negative 1. Equation 3, f12y, we have negative 1. a2y, we have negative 10. Constant is 98.1. Equation 4, we have 0.513 f12x. f12y, we have 1.41. rc, we have negative 0.513. Alpha 2, we have negative 7.5. Equation 5, we have alpha 1, we have 1.03. a2x, we have negative 1. Alpha 2, we have 0.513. Equation 6, alpha 1, we have negative 2.81. a2y, we have negative 1. And alpha 2, we have 1.41. And then our last equation says alpha 2, we have 0.513. a2x, we have 1. Okay, that should be it. This is an issue. These two have to be the same. So something went wrong in here, in one of the, 1,384 steps. But that's the method. I'll look through that later and see if I can find that. Anybody have any questions about that approach? Okay, let's do another one, and this time, step by step, you'll work on it. So for this one, let's say that we have a pin joint connecting one member to the floor at an angle of 45 degrees. And then that's at a right angle to this one. And let's say at this instant, I'll call this member 1, this member 2, A, B, and then the end here is C. We'll say that the angular velocity of 1 is the same thing as the angular velocity of 2. And let's say that's negative 10 radians per second. And we'll say that there's an external couple of positive 100 Newton meters on member 1 and an external couple of negative 100 Newton meters on member 2. And the question is, what's the acceleration of that point C?
How long are they?
Oh yeah, let's say that the length is half a meter and the mass is 5 kilograms. And this, it doesn't take much imagination to figure out how you could use an approach like this for biomechanics calculations. This thing where you have an external couple of m on one body and an external couple of negative m on the connected body is exactly what muscles do. And so what we're doing here, well, in a leg without a body attached to it, but it would just take a couple more steps to include a body on here. We're seeing what accelerations are produced by applying a muscle force to whatever muscle is between. If you think of this as like the lower leg and the thigh, then what we're doing here is applying a muscle extension, like basically turning on the quad muscles or something to straighten out the leg, and seeing what the acceleration is that comes out of it. Okay, so the first step. Yeah. B to C, yes. And there's a pin joint here. Okay, so the first thing you need to do is use Newton's laws for members 1 and 2. So go through that first. So for each one of those, you have to go through those 7 steps. And